This video is a review of complex numbers. So complex numbers can be very useful in physical chemistry. They're very useful especially in quantum mechanics. They can show up everywhere because they have some nice properties that work very conveniently for a lot of things that'll pop up in quantum mechanics. Okay, so the square root of -1 is defined as the number I. So the square root of negative numbers doesn't make sense because a number times itself is the square of a number. So square root of the number is the number you have to multiply times itself to get that number. And negative numbers times themselves give positive numbers. Positive numbers times themselves give positive numbers. So anything that you multiply times itself is going to give a positive number. So negative numbers doesn't make a lot of sense in terms of being able to take the square root of them. That's where imaginary numbers come into play. Because since we define the square root of -1 as I, we can use I and other real numbers to make any number we want, which qualifies as what's called a complex number. So I is in the set of imaginary numbers. We call it an imaginary number. And using I as the base for imaginary numbers and 1 as the base for real numbers, we can make any combination of imaginary and real numbers that we want, and that forms the set of complex numbers. So a number C equals a real number A plus a real number B times I. That gives us any possible complex number. Okay, so as I said, A is some real number which is from -infinity to infinity. B is some real number which is from -infinity to infinity as well. We have various things like the real part of C is A, the imaginary part of C is B, and we can plot these two in a plane as well. And any imaginary number, any complex number we can plot in what we call the complex plane, where the real part A is the x-axis and the imaginary part B is the y-axis. Okay, so let's look at some properties of these complex numbers. So as I said, A is equal to the real part of C, indicated by this RE function C, and that is equal to C plus the complex conjugate of C, C star, over 2. More on that in a second. B is equal to the imaginary part of C, which is equal to C minus C star over 2. Okay, so what is this complex conjugate function? So C star is equal to A minus BI. C is equal to A plus BI. C star is equal to A minus BI. So for the complex conjugate of a number, you take the imaginary part of it and you flip it. I think I need a over 2I down here. Okay, so then we have another concept which is called the magnitude of a complex number. So as I said, you're plotting it in the complex plane here. So a number, if A and B are both positive, we'd have a number C here in the complex plane, and it'd be some distance from the origin. This distance would be called the magnitude of C. So the magnitude of C, actually the magnitude squared, so the magnitude of C squared is equal to C star times C, which if we do our algebra, is going to be A minus BI times A plus BI, which is going to equal A squared minus ABI plus ABI. Well, we got a minus ABI here, we get a plus ABI there, and then we get a minus B squared I squared. Okay, so we can cancel out the minus ABI and plus ABI. So this is going to be A squared, and then I squared is -1, because I is the square root of -1. I squared is -1, so minus B squared I squared is plus B squared. So that gives us that the magnitude of C, kind of its length from the origin in the complex plane, is equal to the square root of its its real part a squared plus its imaginary part b squared. So it's kind of like a Pythagorean theorem in our complex plane here. All right, so that's the magnitude of C. Our complex conjugate C star is where we change the imaginary part to its negative self. So that's a reflection over the x-axis here. We go from a plus bi to a minus bi is C star. Minus C would be minus a minus bi over here in this quadrant. And the complex conjugate of negative C would put the imaginary part back into the positive side. So we'd have negative C star would be minus a plus bi. And all four of those would have the same length because they have the same magnitude of a and b, so a squared and b squared are the same. All right, so using complex numbers, we can do things like factoring polynomials like x squared plus y squared. If we had x squared minus y squared, we would factor that into x minus y times x plus y. But we can't do that for positive numbers, at least until we bring complex numbers into play. So we can factor that as x plus iy times x minus iy. Because you'll notice if we multiply those together, we get x squared from the first term. The inner and outer terms cancel, and you get minus y squared I squared, which just as minus b squared I squared gives us a plus y squared. So we can now factor binomials which are squares, positive squares of each number. Okay, so what else can we say here? We can also say that if b equals 0, then c is a real number. So real numbers are numbers which have no imaginary component. They are along this axis here. So if b equals 0, we're along this x-axis, which in the complex plane represents all real numbers. Similarly, if a equals 0, then c is an imaginary number. This y-axis here is the value where a equals 0, which are purely imaginary numbers. Their only component is their imaginary component. 2i, 5i, pi I, negative 10i, whatever it happens to be. All right, and then as I said, when you take the negative of it, our negative c is going to equal negative a minus bi. Standard rules for polynomials would apply. All right then, and for adding and multiplying complex numbers, we would have c1 plus c2 equals a1 plus a2, the real parts of each of them, plus b1 plus b2, the imaginary parts of each of them, times I. Okay, straightforward, just how you would add other polynomials, now with the added complication that they can have imaginary and real components. And what about multiplication? So c1 times c2, that's going to be a1 plus b1i times a2 plus b2i. So we're going to multiply that as well times a standard kind of binomial multiplication. So that'll be a1, a2 plus, and then b1, b2, I squared is going to give us a minus b1, b2. That's our real component. And then plus, we're going to have a1 times b2 plus b1 times a2. Each of those times I to the first power. So that's how we get our real and imaginary components once we have multiplied c1 times c2. All right, so that's the basics of complex numbers. Complex numbers show up quite frequently in quantum mechanics, which forms the basis of the bulk of 1/2 of an undergraduate of physical chemistry. It's usually one of the PChem courses which is dedicated almost entirely to quantum mechanics, and complex numbers show up in quantum mechanics quite a lot.